Perpendicularity tolerances on a flat surface of a shaft. The tolerance is relative to the datum axis. The feature control frame is connected by a leader terminating on a dot with a model, and attached with an extension line or leader terminating with an arrowhead on the edge of an orthographic view. And reference to datum features of size regardless of material boundary, unless maximum material boundary or least material boundary is shown in the callout. Perpendicularity tolerances for each element on a surface. You need notation of each element beneath the feature control frame when necessary to control individual line elements of the surface. Changes tolerance zone to one that's made of two lines capable of moving across the surface, and constrained in rotation to reference the datum. Perpendicularity tolerance applied to a feature of size, the feature control frame adjacent to the size dimension value, or attached to a dimension line. The diameter symbol is sometimes used for cylindrical features. Reference datum features may be surfaces or features of size. And regardless of feature size, establishes control of the center plane or axis of the feature. And lastly, the maximum material condition or the least material condition establishes a virtual condition and control of a feature surface. Perpendicularity tolerance at MMC for a pin. The tolerance feature at 90 degrees relative to the datum, the primary datum feature, and combined effect of pin maximum material condition, size, and orientation tolerance creates a virtual condition boundary. The pin surface cannot violate the boundary. And the surface method takes precedence over the axis method. The axis method may not provide the same results if a feature has a form variation. Perpendicularity of a feature of size using the surface method. It's used for perpendicularity at MMC or LMC. And the tolerance feature surface must not violate the virtual condition boundary. And it controls orientation and form variables. The feature size and form must also meet the requirements of rule number 1. And additional surface variation may occur as a feature size departs from specific MMC or LMC. Perpendicularity of a feature of size at regardless of feature size axis method. Only method used with RFS, and the axis of tolerance feature within a specified size cylindrical zone, tolerance zone. Pin axis, the axis of the unrelated AME, and establishes no direct control on the pin form or derived median line. Perpendicularity of a feature of size at maximum material condition, axis method. The axis of tolerance features within a cylindrical tolerance zone, and the tolerance zone diameter increases in amount equal to the departure of the pin unrelated to AME from the maximum material condition size. The surface method takes precedence if different results are obtained with the axis method. A perpendicularity virtual condition of a pin with perpendicularity tolerance at maximum material condition. The virtual condition size of the perfect hole that fits over the pin when it is at MMC and in the worst permitted orientation. So it's the virtual condition equals maximum material condition plus the orientation tolerance. The theoretical gauge produced at virtual condition size to check the pin orientation, and verification using the virtual condition is called the surface method. Only checks its perpendicularity and not the pin size or location, and it's related to AME smaller or equal to the virtual condition. The surface and axis methods compared for perpendicularity at maximum material condition. The axis method tolerance zone is based on specified tolerance value at maximum material condition. The surface method has calculated virtual condition for the maximum material condition applications. The methods may give different results when a feature has a form variation. The surface method takes precedence over the axis method. The perpendicularity tolerance at maximum material condition for a hole. The tolerance feature at 90 degrees relative to the primary datum feature. The axis method has a tolerance zone based on a specified tolerance value at maximum material condition. The surface method has calculated a virtual condition for maximum material condition applications. The whole surface cannot violate the boundary, and the surface method takes precedence if different results when a feature has a form variation. Controlling two perpendicular cylinders. No diameter symbol is required on perpendicularity tolerance when applied to a cylindrical feature and a reference to a datum axis. It controls only the orientation, does not control the form when the diameter symbol is omitted, and it includes a diameter symbol if it is desired to control both orientation and form variations. Controlling perpendicularity of slots and rails regardless of feature size. Orientation applied at regardless of feature size on slot establish a control of a center plane. The feature control frame adjacent to the size dimension or attached to a dimension line is acceptable. The slot sides may have a form or angular variation as long as rule number 1 and the size limits are met. The center plane must be within the boundary of the established by two planes of the side surfaces of the slot. Controlling perpendicularity of the slot and rail sides walls. Control of the orientation of the center plane at RFS does not directly control two slot side walls. Control of the orientation of one side wall and a slot size affects both walls. Perpendicularity tolerance applied to each slot surface directly controls the orientation of each of the walls. Notation 2 times above the frame indicates it applies to both surfaces in the model. And 2 liters indicate that the frame applies to both surfaces in an orthographic view. And the tolerance zone on each surface is independent of each other. Controlling perpendicularity for slots and rails at maximum material condition. Perpendicularity tolerance at MMC establishes a virtual condition that the slot sides cannot violate for the surface method. A surface method takes precedence if the difference between results are obtained with the axis method. And the slot center plane must be within the perpendicularity tolerance zone for the axis method. Angularity tolerance establishes control of any flat surface or feature of size at angles other than parallel or perpendicular. It may also be applied on parallel and perpendicular features. Always reference to one or more datums when you're using this geometric form. Angularity tolerance is applied to a flat surface, the feature control frame attached with the leader, terminating with a dot on the surface when using them in a model, and it's attached with the leader or to extension line from the surface in an orthographic view. Angle dimensions defining the surface orientation must be basic, and a queried angle between a datum feature and the tolerance feature establishes a basic angle in models. No angles assumed other than perpendicularity and parallelism in orthographic views. The angular tolerance zone. It controls both surface and form orientation, does not control location, and is defined by two parallel planes. Only rotational degrees of freedom relative to reference datum features constrain the tolerance zone. The angularity tolerance of a surface on a one datum feature reference only constrains rotational degrees of freedom for orientation tolerance zone relative to the datum feature. The surface location not controlled by the angular tolerance and defined by direct tolerance dimension or profile tolerance. The workpiece on a sign bar and a dial indicator is passed across it to verify. Part orientation may be changed if reading is too high. The angular tolerance on a surface, two datum feature references. So it constrains all rotational degrees of freedom for the tolerance zone, and the flat primary datum feature constrains two secondary constrains the remaining one. So here we have a datum A and B that's being controlled by this controlled frame. And the same verification method, but the secondary datum feature must be properly orientated on the sign bar. And the part is rejected or reworked if the reading is too high. Angularity tolerance applied to a feature of size establishes the control of the center plane or axis of feature of size at regardless of feature size. It establishes the control of a feature surface at MMC or LMC, and the feature control frame adjacent to the size dimension value or attached to a dimension line. Tolerance zones and datum constraints are the same as perpendicularity and parallelism, and any basic angle can include 0 or 90 degrees. Tangent plane, mating part angles affected by the amount and location of surface variations, can be controlled by specifying orientation tolerance applicable to a tangent plane. Do not use if the orientation of the tolerance on the surface is adequate and the tangent plane on the tolerance zone of the surface may not be within. Combined form and orientation tolerances. Multiple single segment feature control frames applied to a single feature. Control orientation to one value and a form a smaller value, and only required when maximum allowable form tolerance is less than the allowable orientation tolerance. It's also needed when orientation is applicable to a tangent plane. Orientation also controls form on surfaces. Orientation and form on surfaces. Any orientation tolerance may be specified with an appropriate form tolerance. Multiple feature control frames stacked together can be connected to a single leader terminating with a dot on the surface boundary in a model, and may have separate leaders for each feature control frame. And it's commonly organized to place larger tolerance zones first. Orientation and form on features of size regardless of feature size. RFS, orientation tolerance, control axis or center plane of unrelated AME. The compliance checked by finding the unrelated AME and ensuring the axis meets the tolerance. RFS form tolerances control derived median line of a feature or plane. Compliance is checked by finding centers along a pin and determining if it's within tolerance. Form and orientation tolerances at RFS accumulate. Orientation and form of features of size at MMC. Both MMC, orientation, and form tolerances create a virtual condition boundary. The feature surface cannot violate the boundary, and both controlled surfaces both surfaces control the form. It's possible to show form tolerance must be less than orientation tolerance, and maximum material condition orientation and form tolerances do not accumulate because the form is also controlled by orientation maximum material condition. All right, in summary, in this lesson, you learned how orientation tolerances in GD&T control the angular relationships of a feature relative to one or more datum features, ensuring parallelism, perpendicularity, or angularity. You saw how orientation tolerances are applied using a feature control frame and how they govern surfaces or features of size based on their specification. Unlike simple plus and minus tolerances, orientation tolerances provide precise and unambiguous control, making them essential for accurate part design and manufacturing. Okay, in conclusion, by the end of this lesson, you were able to identify, apply, and interpret orientation tolerances, complete orientation tolerance specification, including 1 and 2 datum feature references, explain the effects of material condition modifiers when orientation tolerances are applied to features of size. Also, you calculated the virtual condition for internal and external features of size to which an orientation tolerance is applied. And complete the tolerance specifications that include orientation and form requirements on a single feature. This concludes this lecture, and thank you for listening, and I'll catch you on the next one.